In this last video, we will discuss the proof of the proposition 8. And in order to prove the first statement, it will be enough to show P, which is obtained removing the units from O, forms an ideal in a local ring. Because then obviously we can see that it's a unique maximal ideal in O. And this gives us that O is a local ring. And first, we'll see that for every x in P and every z in O, their product is element in the maximal ring. So that means we need to see that x times z in O this is true because O is a ring. And we also need to check that this product is not unit, because otherwise, if we suppose that it has a multiplicative inverse omega in O, we also obtained the multiplicative inverse x as omega times z in O, and this gives us contradiction because we choose x in P and it is not unit. And in order to prove that x is closed under addition, we will use this first statement as follows. Here I claims to see this summation, or it can be stated as the product of x and 1 plus y over x. It's enough to see that 1 plus y over x in O, because from 1 we can say that it's in P. And for this purpose, without loss of generality, let me suppose that x over y or y over x, in this case, if you consider this factorization, let me say y over x in O, and since O also contains 1, we see that this multiplication in O. To prove the second statement, which says x in P if and only if its inverse is not in O, it's enough to apply the definitions of a valuation ring and the maximal ideal that is defined in the first statement. And finally, we want to see that all algebraic elements also is in an evaluation ring. And to prove that we suppose not, so that means we suppose there exists an algebraic element which is not in O. And by the definition of evaluation ring, this forces that Z inverse should be in O. On the other hand, since Z is algebraic, Z inverse is also algebraic. We can consider a non-trivial polynomial equation that contains Z inverse as a root. Since the coefficients from K without loss of generality, we can consider the last term, constant term, as 1. And by rearranging this equation, so we will take this summation on the right hand side. And since each term will contain Z inverse, we can write this equality as minus Z inverse time AI Z inverse to the R minus 1 plus A1, and multiplying this equation by Z, we see that Z can be expressed in terms of this polynomial. But we suppose that Z inverse in O, and we know that K lies in O. This shows that the right hand side of this equation is in O. But this gives us contradiction with our assumption. And this shows that K tilde the constant field is a subset of evaluation ring. And finally, in order to see that K tilde has trivial intersection with the maximal ideal P, we suppose otherwise. And since the full constant field lies in O, we see that X inverse is also algebraic. Moreover, X is unit. But this gives us contradiction because we also suppose that X in the maximum ideal P. So it cannot be unit. Okay, these are all I want to say for the discussion session on Tuesday. And regarding the topic we covered in the discussion session, I can ask you the definitions of an algebraic function field. What are the examples we have seen? and to talk about a bit more on the valuation ring. And hope to see you all on Tuesday. Bye-bye.